All right, let's look at some real problems here. So I can't remember exactly which ones I assigned from this table in the textbook, but we can do a representative sample. So I'm going to do number one. So here we've got, it's basically just giving us a whole bunch of different possibilities. But I'm going to do this setup for number 11 here. So number 11, it tells me that I have a P of 8 centimeters. It tells me I have a convex mirror where the magnitude of the focal length in centimeters is 10 centimeters. Well, convex might have a 10 centimeter focal length, but it's a negative 10 centimeter focal length because it's convex. So they didn't tell me that, they're just telling me it's that. So I need to remember that convex mirrors have a negative focal length. And then it asks me to find out a variety of things. So the first thing it wants to know is, what is R? Well, I'm going to remember that the focal length is equal to, in the case of a convex mirror, negative R over 2. So R is just going to be 20 centimeters. And it's a positive, right? The focal length is negative. The radius of curvature is not. And then part B, it says, what's the image distance? So then I'll use my mirror equation to determine the image. So I'll do 1 over the image distance is 1 over the focal length minus 1 over the object distance. 1 over the image distance is equal to 1 over negative 10 centimeters. It's a negative focal length, so I need to put it in as a negative. And then I say 1 over the object distance, which is 8 centimeters. Now, I can leave these things in centimeters as long as I'm willing to accept my answer in centimeters, and I am. So you can leave things in centimeters as long as they're all in centimeters. And that will work out in this chapter. So negative 10, x to the minus 1, minus 8 to the x minus 1. Now this tells me, this answer says negative 0.225. This is not the image distance. This is 1 over the image distance. The actual image distance is the inverse again of that, or negative 4.44 centimeters. So make sure that you remember that you have to flip things back over again. Part C says, what's the magnification? So the magnification is negative I over P. So I'll say negative 4.44 centimeters over P, which was 8 centimeters. So this is a positive 0.556. So this is a positive magnification. So first of all, I had a negative image distance. That tells me this is a virtual image. This is a positive magnification. So this tells me it's not inverted. And it's less than it's less than 1, so it's smaller. So when I look up here, where it says part C, I got the magnification, but then it says, is it real or virtual? It's virtual because I have a negative I. I is negative. It says, is it inverted or not inverted? It's not inverted because m is greater than 0. It's a positive magnification. It doesn't ask me smaller or larger, but it does ask me what side it's on, and this is a mirror. So, and I have a virtual image. So for part E, it's virtual. It means it's on the opposite side. All right, there's nothing over there. I can't recreate this exactly in this simulation, but this is a simulation that allows me to do this sort of stuff. So I've got, this actually can be both. This is a concave mirror where my object is on this side. And then if I drag my object to the other side, now I have a convex mirror. So I already have it set up with a focal length of 10 centimeters. If I try to get my object to 8 centimeters, it doesn't quite let me do exactly 8. It does 8.1 and 7.8. So this is pretty close, but this is what we're talking about. We have an object here, and then we have an image forming here, right? And we can see that 8.1 and 4.33, if I could make this 8, it would be essentially that 4.44, but it's not letting me get to that thing. So, but that's where we're at in terms of this. So we're making an image which is inside it. You can see it's not inverted, it's smaller, and it's inside. It's on the opposite side. Number 10, let's look at that one. So number 10, I now have an image distance of 15. Now I have a concave mirror, and it also has a focal length of 10. So I've written that down here. P is plus 15. This is a concave mirror. They told me the magnitude of the focal length is 10, but this is also a positive. This is a concave, so we have a positive focal length. And so part A, again, says what is R? R is just 2 times the focal length, so it's again 20 centimeters. For B, now we want to know the image distance, so 1 over I is 1 over F minus 1 over P. So 1 over 10 minus 1 over 15. I'll do that really quickly. So 10 inverse minus 15 inverse. Inverse. Oh, inverse yet. That's extremely small. It's 0.03333 per centimeter, but again, I need to do the inverse of that, and I get 30 centimeters. Then my magnification is negative I over P. So negative 30 centimeters over 20 centimeters, I get a negative 1.5. And now it starts to ask me, so for D, real or virtual? Well, I have a positive image distance, so this is a real image. I is positive. For part E, it says, is it inverted or not inverted? My magnification is negative, so it's inverted. It's an upside down image. And then finally, F, it's asking me, is it on the same side or the opposite side? It's a real image, so it's on the same side because it's a real image. So let's see if we can make this situation. I need to have a convex instead. I need to change my focal length to 15. Let's see if it'll let me do 15. And then I want to put my, it's 10. Focal length is 10. And then I want to put my object at 15. There. So I have my object at 15. My image does show up out here at 30. So over here at 30, it is inverted, right? It's upside down compared to my original object, and it's definitely larger as well. It doesn't ask us that, but it is larger. It's 1.5 times as large, and it's on the same side of the mirror as the object. This is a sim called simbucket.com. It's lenses and mirror, if that's any help for you guys to go through and mess around with it. Let's do one more of these. So number 13, I'm not going to go back up and look at what they're saying. We'll just go with the numbers that I've already written down here. They tell me that the object distance is 12 centimeters. They tell me, again, I have a concave mirror, but now my focal length is 18. So again, R is just going to be twice that or 36 centimeters. B, the image distance is still 1 over the focal length minus 1 over the object. So I have 1 over 18 minus 1 over 12. Now this comes out to be a negative value, 0.027777 per centimeter. So when I do this image distance, when I do the inverse of that, I get a negative 3.6 centimeters. That's virtual. Right, when we get to that question, we have a negative image distance, so it's definitely virtual. C, our magnification is negative I over P, so negative 3.6 centimeters over 12 centimeters. Oh, 36, sorry, that's 36 here. Pardon me, guys, it's 36. My calculator knows more than I do, as usual. 36. So this ends up being a magnification of 3, a positive 3. So this is not inverted. This is upright. It's a positive magnification, and it's larger, 3 times larger. So when we go through them, our part D says, is it a real or a virtual? We already said this. It's virtual because I is negative. E, is our magnification is positive, so it's not inverted. It's the opposite of what we had in the earlier problem. And then F, this is a virtual image, so it's on the opposite side. So let's see if that's what happens when we go through and do this with our simulation. So our focal length should be 18. Let's see if it'll let me do 18. Won't let me do quite at 18. We'll roundabouts it. We'll do the 17.5, and then a P of 12. So something like this. And we do see that our image is huge. It's definitely virtual. It's on the opposite side of our mirror from our object. It's not inverted. It's definitely larger, and it's over there. Okay. We could go through and play in all different games here and try all different combinations, but I will cut to the chase and tell you that it turns out that a convex mirror, which is when I have my image, my object over here, a convex mirror, no matter how far away I put this, I always end up with a virtual image. You don't have it, it gets smaller and smaller the further I put away, and it tries to get larger as I get closer. I can change my focal length here. And again, I can't ever get anything but a virtual image. My image is always on the opposite side here. So even if I have, focal lengths, no matter what, I always have a virtual image. So mathematically, that means that our image has a negative number. You also always make smaller images. Notice that there's no way that this ever gets as big as my object. No matter what my focal length is, I can never get anything as big as my object. You can get almost as big, but you just don't ever get as big. So it's a small thing. This is like those garden mirror ball things, that you look into. You always look smaller inside of it. And again, it's also not inverted. So a convex mirror makes a virtual, smaller, non-inverted image. Concave mirrors can do different things. So a concave mirror, let me make my focal length a little bit more reasonable here. So a concave mirror, if your object is inside the focal point, you get a virtual image. So if your object distance is less than your focal length, so if I'm inside here, I get a virtual image, and it's larger, not inverted. But if it's at the focal point, exactly, there actually is here, I'm right at the focal point, and it says image distance infinity, image height negative infinity. There is no image if you're at the focal point. Now, if I go outside the focal point, now my image is way over there. I actually have we'll make this here. So I'm in between my F and my delta F. I now have real images. So if P is larger than F, I have a real image. If it's between F and 2F, which is really the center point, my image is larger than my object. If I flip the other way, now I'm outside of 2F. Now my image is smaller than my object. If I'm actually at 2F, they're exactly the same size. So this has two different, or really three different things. So it can make a virtual image if your P is inside of F. It doesn't make anything if it's at F. It makes a large real image when you're at between F and 2F, and it makes a smaller real image when your P is greater than 2F. And we can try to summarize these all up in this table, and then I'll move on in the next video and talk about some other stuff. So a plane mirror makes an image. When I talk about location, they mean either opposite side or same side. For a plane mirror, it makes an image on the opposite side. It's a virtual image, and it's oriented, not inverted, right? Or that would be kind of annoying in a plane mirror or flat mirror for us to do that. A plane mirror doesn't really have a focal length. It has sort of an infinite focal length. So it doesn't have a focal length or a radius of curvature. It does have negative sign or negative image distance, and it has a positive magnification. A concave mirror, right, which is what we're talking about here, a concave mirror, if we're inside of the focal length, inside of capital F, then we're going to get an image which is formed on the opposite side, and it will be a virtual image, and it will be not inverted. For a concave mirror, the focal length is positive and the radius of curvature is positive. The image for this, if we have virtual, then we have a negative image distance and we have a positive magnification. It doesn't mean, I'm not saying it's larger, I mean it's positive in the sense that it's not inverted. So these two things basically go along with this. Positive magnification means that it's not inverted. If the number is bigger than 1, that tells you it's larger. If it's smaller than 1, it tells you it's smaller. If we're outside, if P is outside of F, then we get an image on the same side of the mirror as our object. It's a real image, and it is inverted. This still has a positive focal length and a positive R, but now our image is positive and our magnification would be negative in the sense that it's telling us that it's been flipped upside down. For a convex mirror, no matter what we do, we get an image which is on the opposite side. It's always virtual. It's always not inverted. The sign of F is negative. The sign of the radius of curvature is positive. And then the sign of the image distance is negative, and the sign of the magnification is positive. Okay, I'll come back and, well, actually, let me quickly just say this. It is also possible, but I'm not going to have you do it. You may have done this in some previous class. It is also possible to find the location of images using ray tracing. and they show the rays in this image here and discuss what they all are. So does this simulation. Ray 1 is a ray that's initially parallel to the central axis. So this is our top line up here, and then it reflects back through the focal point. Ray 2 is a ray that goes from the top of your image through the focal point until it hits the mirror, and then it reflects back parallel to the central axis. So they're showing us those two in this top picture as well. There's also a ray that goes straight from the top to the center, to this basically where the central axis hits the mirror, and then bounces back off again in that same sort of direction, and that basically back along that and makes a third ray. Notice that all three rays are converging at the same place. The top of this arrow is sending out these three rays, and they're converging at the top of the image of the arrow. And there really is light really there. If I did a convex, it's a little bit more complicated to draw these. For the first ray, again, we go parallel to the central axis. This light ray is now supposed to go through the focal point, but the focal point's on the other side. And so we have the imaginary part of it that goes through the focal point, and it actually reflects off and goes off to this direction. The dashed line is telling us there's not really light there. Ray 2 is trying to go straight to the focal point, but as it goes along to get to the focal point, it then hits the mirror, and so we just have it basically will reflect back parallel. So this line would have extended all the way to the little f, but instead, once it hits the mirror, it goes off parallel to the central axis. And then the third ray is again trying to go towards the center, and once it gets there, it reflects back off away. Notice that here, where our image is, we have these dashed lines. That tells us there's not really light there. This is a virtual image. This is the difference between a virtual image and a real image. When you draw the ray tracing, you'd have real solid lines on the side where there's really light and dashed lines where there's not light. So these are all virtual images converging into this arrow. Whereas if I flip over to the other side, again, at first I have a virtual image even for a concave, but then once I get outside of F, I have real light rays that are actually converging at this location. If I put a detector there, a camera or film, or even my eyes, I would see that there's really, really light interfering there, or interacting there, or converging at that location. Again, we're not going to do any ray tracing. For us, we're pretty much always just going to use our mathematical equations to determine our our image distances or object distances or magnification. So again, we'll use these equations instead of doing ray tracing. All right, I'll do some more in the next video.